Good morning, everyone. I am delighted to welcome you to this overview of symmetric cryptography. My name is Dr. Hodges, and today we are going to embark on an exciting journey into the world of secret key encryption algorithms. Symmetric cryptography forms the foundation of modern cryptographic practices, playing a vital role in securing data confidentiality, integrity, and authenticity. Throughout this lesson, we will explore the fundamental principles, unique characteristics, and practical applications of symmetric cryptography. I want to ensure that you not only grasp the conceptual framework, but also gain practical insights into this essential cryptographic technique. So let's dive right in and explore the intricate workings of symmetric cryptography. Together, we will uncover how it enables us to safeguard sensitive information in a world where data security is of utmost importance. In my experience, the majority of my students have never taken a cryptography course before and feel overwhelmed. However, the reality is that you use cryptography without even realizing it. So don't worry, take a deep breath, pair this video with the readings, and feel free to watch it as many times as you need. Now, let's begin by delving into the core concepts that make symmetric cryptography such a powerful tool in the realm of data protection. Transposition and substitution cryptography are two different methods used in encoding messages. Transposition encryption involves rearranging the letters of a message, while substitution encryption replaces each letter with a different one. Both techniques are significant in ensuring message security. Confusion and diffusion are two techniques used in cryptography to enhance the security of encrypted messages. Confusion involves replacing letters in the plain text with different letters in the ciphertext, making it difficult for anyone to decipher the message based on letter frequency analysis. Diffusion, on the other hand, ensures that changing one character in the plain text will have a widespread impact on the ciphertext, making it harder to discern patterns or relationships between the two. When these techniques are employed correctly, they create an avalanche effect, meaning that even small changes in the original message will result in significant changes in the encrypted output. There are two main types of symmetric ciphers: stream ciphers and block ciphers. The difference between them is a simple concept. Stream ciphers encrypt or decrypt individual bits one by one, while block ciphers operate on a group or collection of bits at a time. Understanding this distinction is essential for comprehending cryptography and its applications. There are certain use cases where one method is preferred over the other. As a security professional, it is important to be aware of the advantages and disadvantages of each method, as well as the risks associated with designing any cryptographic system. Like all courses, there are several definitions that we need to review. While I haven't included all of them on my slide, I will mention most of them. Additionally, you can find these definitions in your reading materials and most published literature from NIST. Cryptography is the scientific process of transforming information into an unreadable form. On the other hand, cryptanalysis involves the study and practice of identifying vulnerabilities in codes. An algorithm is a set of steps or procedures used to achieve a specific outcome. A cipher is a technique used to encode characters in order to conceal their value. Deciphering, in contrast, is the process of decrypting encrypted text. Plain text refers to information transferred or stored without cryptographic protection. Cryptology, as a field of study, encompasses both cryptography and cryptanalysis. A cryptosystem is a combination of components that forms a system for encryption and decryption. Lastly, key clustering occurs when different keys produce the same ciphertext. Typically, the algorithm does not possess the secret piece, which is the secret key. The key comprises a significant collection of random numbers. A primitive function within an algorithm is called a primitive mathematical function. The key instructs the process of encryption, transforming plain text, readable, into ciphertext, unreadable. The key space represents a vast collection of values from which the algorithm chooses the key for generation. The greater the value within the key space, the more space is available, resulting in a stronger algorithm and enhanced security. Secret key, shared key, same key, single key, and session key are all terms used to describe a specific cryptographic key that is ideal for bulk encryption. This form of encryption is significantly faster than asymmetric cryptography. The key characteristic of this type of encryption is that both parties involved in the communication must share and use the same key. Why do we use symmetric cystography? Well, it has several major advantages. Advantages include being less computationally intensive, producing smaller file sizes, allowing for faster transmissions, and being cheap. While most executives, who often lack an understanding of cybersecurity and cryptography, may not comprehend the technical aspects, they do understand the benefits of something that is cheap, easy, and fast. However, there are also some disadvantages to using symmetric cryptography. The disadvantages are as follows. Exchanging the shared secret key is often impractical and insecure due to obvious reasons. Trust between parties sharing the key may be lacking, leading to confidentiality but not authenticity. Keys must be managed as the user population grows, resulting in an increase in keys. The formula NN12 demonstrates the growth of key size. Symmetric cryptography does not provide authentication or non-repudiation. Despite these inherent problems with symmetric cryptography, it still functions effectively. As a solution, a hybrid format combining symmetric and asymmetric cryptography is used. More details on asymmetric cryptography will be discussed in a separate video. Let's dive into the details of how the binary code uses XOR, OR, and AND arguments to combine ones and zeros, with a specific focus on the exclusive OR, XOR binary function as an example on my slide. Binary code. Binary code is a system of representing data using only two digits, 0 and 1. It is the foundation of digital computing and allows computers to process and communicate information. Each digit is called a bit, short for binary digit. This is not addition, subtraction, division, or multiplication. It is combining ones and zeros. XOR, exclusive OR. The exclusive OR, XOR, is a binary logical operation that combines two bits and returns a result based on whether the bits are the same or different. To understand how XOR works, let's consider the following examples. XOR of 0 and 0. When both bits are 0, the XOR operation returns 0. XOR of 1 and 0. When one bit is 1 and the other bit is 0, the XOR operation returns 1. XOR of 0 and 1. Similar to the previous case, the XOR operation returns 1. XOR of 1 and 1. When both bits are 1, the XOR operation returns 0. In essence, the XOR function returns 0 if the two bits being compared are the same, and 1 if they are different. It is important to note that XOR operations are symmetrical, meaning that XORing A with B will produce the same result as XORing B with A. This property makes XOR useful in many applications, including cryptography.OR, inclusive OR. The OR operation, often referred to as the inclusive OR, is another binary logical operation used in the binary code. The OR operation returns 1 if at least one of the bits being compared is 1. Let's consider some examples. OR of 0 and 0. When both bits are 0, the OR operation returns 0. OR of 1 and 0. When one bit is 1, the OR operation returns 1. OR of 0 and 1. Similar to the previous case, the OR operation returns 1. OR of 1 and 1. When both bits are 1, the OR operation returns 1. In summary, the OR function returns 0 if both bits being compared are 0, and returns 1 if at least one of the bits is 1. And the AND operation is another binary logical operation that combines two bits and returns a result based on whether both bits are 1. Let's consider some examples. AND of 0 and 0. When both bits are 0, the AND operation returns 0. AND of 1 and 0. When one bit is 0, the AND operation returns 0. AND of 0 and 1. Similar to the previous case, the AND operation returns 0. AND of 1 and 1. When both bits are 1, the AND operation returns 1. In a nutshell, the AND function returns 1 if both bits being compared are 1 and returns 0 otherwise. These logical operations, XOR, OR, and AND, are fundamental tools in binary coding, allowing for various manipulations and transformations of binary data. They form the basis of complex computations and are integral to digital systems, including computer processors, communication protocols, and cryptographic algorithms. Many traditional and modern-day symmetric algorithms involve the use of these operations. If this is new to you, don't be overwhelmed. Like I have stated before, you can always go back and watch this video again. But if you are studying for a CISSP or other cryptography certification, I would expect you would need to understand these operations. Key management is an essential aspect, as the key plays a crucial role in instructing the algorithm on how to function effectively. Increasing the key size results in generating more values for the key and subsequently enhances the strength of the algorithm, thereby increasing the difficulty of the work factor. It is important to utilize the entire key space and implement the use of random key generation, also known as IVs. To ensure optimal security, strong keys should be employed, which are longer in length compared to the message itself. Additionally, it is imperative to establish efficient key management practices and ensure the implementation of robust security measures. DS is not an algorithm, it is a standard. DEA, on the other hand, is the algorithm that satisfies the DES standard. I would like to clarify this for those who are preparing for a test. Based on IBM's Lucifer algorithm, DES, Data Encryption Standard, is a widely utilized symmetric encryption algorithm. It operates on a 64-bit block system and employs a 56-bit key with an additional 8 bits for parity. However, over time, DES has been found to possess vulnerabilities and is considered relatively easy to break using modern computational resources. To address these concerns, a more secure version called 3DES, triple DES, was introduced. 3DES enhances DES's security by applying the DES algorithm 3 times to each data block. This triple encryption process significantly increases the key size to 168 bits, effectively mitigating security risks. Furthermore, 3DES incorporates an additional 24 bits for parity to ensure data integrity. Despite its heightened security, the extensive key size and computational complexity of 3DES have resulted in its gradual replacement by more contemporary encryption algorithms. It is worth noting that DEA, Data Encryption Algorithm, is a variant of DES developed by the United States government for non-classified data encryption purposes. DEA employs the same encryption structure as DES, but utilizes shorter key lengths of 40 or 56 bits. Although DES, DEA, and Lucifer have played significant roles in the progression of cryptography, the widespread adoption of more robust and efficient algorithms, such as the Advanced Encryption Standard, AES, has superseded their usage in most modern implementations. DES operates by applying 16 rounds of substitution and transposition on data blocks of 64 bits. It uses a 56-bit key with 8 additional bits used for parity. DES supports various encryption modes for different applications. One of these modes is ECB, Electronic Code Book, which encrypts each 64-bit data block independently, making it vulnerable to certain attacks due to the deterministic nature of the encryption. To address this limitation, the cipher block chaining, CBC mode, was introduced. CBC XORs the previous ciphertext block with the current plaintext block before encryption, introducing randomness and enhancing security. Another mode, cipher feedback, CFB, enables the encryption of individual bits or smaller units, using them as feedback to encrypt subsequent bits or units. CFB mode is suitable for streaming data applications. The output feedback, OFB mode, similar to CFB, operates on smaller units, but transforms them using encryption rather than encryption feedback. OFB is a suitable choice when error propagation is a concern, since it does not rely on previous encryption results. In addition, the counter mode, CTM, transforms a unique value, nonce, and a counter into a key stream, which is then XORed with the plaintext. CTM is favorable for parallel processing and allows random access to different parts of the encrypted data. These various modes of operation provide flexibility in choosing the appropriate encryption scheme for specific requirements and applications, considering factors such as security, parallel processing, and data integrity. It's important to note that while DES and its various modes were widely used in the past, they are now considered outdated and have been replaced by more secure and efficient algorithms, such as the Advanced Encryption Standard, AES. Here is an overview of the DES modes of operation I discussed on the previous slide. Let's review a few of them again. One of these modes is ECB, Electronic Code Book, which encrypts each 64-bit data block independently, making it vulnerable to certain attacks due to the deterministic nature of the encryption. Cipher block chaining, CBC mode, was introduced. CBC XORs the previous ciphertext block with the current plaintext block before encryption, introducing randomness and enhancing security. Cipher feedback, CFB, enables the encryption of individual bits or smaller units, using them as feedback to encrypt subsequent bits or units. CFB mode is suitable for streaming data applications. The output feedback, OFB mode, like CFB, operates on smaller units, but transforms them using encryption rather than encryption feedback. OFB is a suitable choice when error propagation is a concern, since it does not rely on previous encryption results. The counter mode, CTM, transforms a unique value, nonce, and a counter into a key stream, which is then XORed with the plaintext. CTM is favorable for parallel processing and allows random access to different parts of the encrypted data. These various modes of operation provide flexibility in choosing the appropriate encryption scheme for specific requirements and applications, considering factors such as security, parallel processing, and data integrity. When reviewing a system's security or deciding what level of encryption to implement, it's important to understand these modes of operation. Random values are often used in conjunction with cryptographic algorithms to ensure that patterns are not created in the resulting ciphertext. These random values, also known as initialization vectors, IVs, or nonces, are typically generated and used for encryption alongside the keys. Without the use of random values, if the same plaintext is encrypted multiple times with the same key, it will generate identical ciphertexts. This can lead to potential vulnerabilities, as attackers may be able to detect repetitions and identify patterns in the encrypted data. To mitigate this issue, random values are introduced during the encryption process. These values are used as inputs to the cryptographic algorithm alongside the key in order to create unique transformations for each encryption operation. As a result, even if the same plaintext is encrypted multiple times with the same key, the presence of different random values ensures that distinct ciphertexts are generated. By incorporating random values, cryptographic algorithms enhance the security of the encryption process, making it more resistant to cryptanalysis techniques that rely on detecting patterns and repetitions in the ciphertext. It adds an additional layer of randomness and unpredictability, making it harder for adversaries to deduce information about the plaintext or the keys used. The proper generation and management of random values, such as using strong random number generators, is critical to ensure their effectiveness in preserving the security of cryptographic systems. In certain scenarios, where the encryption of small amounts of data is required, stream ciphers can be a suitable choice to ensure that errors do not significantly impact the encryption process. Stream ciphers operate by encrypting data bit by bit or byte by byte, which makes them well suited for applications that involve real-time or fine-grained encryption of data streams. Stream ciphers generate a key stream that is combined with the plaintext using the XOR operation to produce the ciphertext. This key stream is typically generated from a key, and in some cases, an initialization vector, IV, or a nonce. One advantage of stream ciphers is that they provide error propagation containment. In other words, if an error occurs during transmission or storage, it will generally only affect the specific bit or byte where the error occurred, rather than propagating through the entire ciphertext. This characteristic can be advantageous in situations where the reliability of the communication channel or storage medium is not guaranteed. By encrypting small amounts of data using a stream cipher, any errors that may be introduced in the transmission or storage process are less likely to have a cascading effect on subsequent parts of the encrypted data. The decryption process can still recover the correct plaintext, even if some errors were encountered in the ciphertext. However, it is important to note that the use of stream ciphers for encryption should always be guided by a thorough understanding of the specific security requirements and potential vulnerabilities. Stream ciphers, like any cryptographic algorithm, need to be properly implemented and managed to ensure their effectiveness and resistance against potential attacks. I want to delve deeper into DES, which is a Feistel cipher. The Feistel function divides the plain text block into two parts, LO and RO. The round function is applied to one of the halves, with the details of each round varying based on the mathematical operations of the algorithm. The resulting output is then XOR'd with the other half. This process is repeated 16 times. Many symmetric ciphers utilize this function, and having a basic understanding of how this operation works provides a better comprehension of cryptography as a whole. So, DES was broken in 1998. We tried using 2DES, which had the same work factor as DES, which led us to 3DES. Eventually, AES was born. Until AES was released, they attempted to enhance DS with a few modifications, such as DSX, involving key whitening, by XORing a key with the text before, after, or both the round function. They also extended DS, utilizing 48 rounds in 4 modes, DS-EE2, DS-EDE2, DS-EE3, and DS-ED3. Due to DES being broken, we needed to move on to a new algorithm, which resulted in the selection of AES. AES is a symmetric block cipher that is based on the Rindale algorithm and is compliant with the FIPS 197 standard. Instead of using a Feistel network, it utilizes a substitution permutation matrix known as a 4x4 column matrix state. To generate round keys, the key expansion process is employed. The cipher operates in multiple rounds, with each round consisting of the following steps. Substituting bytes. Each byte is replaced with another byte based on a lookup table. Shifting rows. The rows of the state matrix are transposed. Mixing columns. A mixing operation is applied to the columns of the state matrix. Adding the round key is XOR'd with the state matrix. In the final round, the steps of substituting bytes, shifting rows, and adding the round key are repeated. The number of rounds varies depending on the key size, with 10, 12, or 14 rounds being performed for key sizes of 128, 192, or 256 bits, respectively. The block size for AES is always 128 bits. This brings us to the net of this lecture. Let's briefly review. Data Encryption Standard, DES. Key size, 56 bits, with an additional 8 bits for parity. Block size, 64 bits. Rounds, 16 rounds of substitution and transposition. Feistel network structure. Triple DS, 3DS. Key size, 168 bits, using 3 56-bit keys. Block size, 64 bits. Rounds, 3 consecutive DES operations, typically 48 rounds if all 3 keys are used. Advanced Encryption Standard, AES. Key size, 128, 192, or 256 bits, depending on the variant. Block size, 128 bits. Rounds, 10, 12, or 14 rounds, depending on the key size. Or Blowfish, key size, variable, up to 448 bits. Block size, 64 bits. Rounds, variable number of rounds, typically 16.5. Twofish, key size, variable, up to 256 bits. Block size, 128 bits. Rounds, variable number of rounds, typically 16 for a 128-bit key. Serpent, key size, variable, up to 256 bits. Block size, 128 bits. Rounds, 32, round 7. Cast, key size, variable, ranging from 40 to 128 bits. Block size, 64 bits. Rounds, variable number of rounds, typically 12, 16, or 32.8. Skipjack, key size, 80 bits. Block size, 64 bits. Rounds, 32, rounds 9. International Data Encryption Algorithm, IDEA, or Tiny Encryption Algorithm, TA. Key size, 128 bits. IDEA, 128, 192, or 256 bits. TIA. Block size, 64 bits. IDEA, 64 bits. TIA. Rounds, 8.5 or 16. IDEA, 64. T, 10. Rivas Cipher 4, RC4. Key size, variable, ranging from 1 to 256 bytes. Block size, stream cipher, no fixed block size. Rounds, not applicable, stream cipher. 11. RC5, key size, variable, ranging from 0 to 2040 bits. Block size, 32, 64, or 128 bits. Rounds, variable number of rounds, typically 12, 16, or 20. 12. RC6, key size, variable, up to 2040 bits. block size 128 bits, rounds variable number of rounds, typically 20 or 24.13, simple highly advanced Rindale-based key alternating cipher, SHARC, key size variable up to 512 bits, block size 64 bits, rounds variable number of rounds, typically 8, 12, or 16. It is important to note that while these summaries provide a general overview, the mentioned algorithms may have various modes of operation, key scheduling mechanisms, and other aspects that further impact their implementation and usage in specific scenarios. In conclusion, this class has provided a comprehensive exploration of various encryption algorithms and their essential characteristics. We have examined symmetric ciphers, including well-known ones such as DES, 3DES, AES, Blowfish, and RC4, as well as lesser-known yet equally important algorithms like Serpent, Cast, and Skipjack. Additionally, we have covered block sizes, key sizes, rounds, and structures, which play crucial roles in determining the strength and efficiency of each cipher. Throughout this course, we have learned about the importance of random values and initialization vectors in preventing patterns in ciphertext creation. Stream ciphers were also discussed as a viable option for encrypting smaller amounts of data, ensuring minimal error propagation during the encryption process. Furthermore, we have gained insight into the relevance of strong key generation and management for maintaining the security of cryptographic systems. It is essential to understand that while symmetric ciphers have their merits, they must be selected and implemented with careful consideration of the specific security requirements of each application. Keeping up with the advancements in encryption standards, such as transitioning from DES to AES, is crucial to maintain robust protection against evolving threats. By studying these ciphers, we have developed a deeper understanding of the fundamentals of encryption and its significance in safeguarding sensitive information in various contexts. Armed with this knowledge, we are better equipped to make informed decisions when it comes to encryption methods, ensuring secure communication, data privacy, and confidentiality. I encourage you to continue watching all the episodes in this series to truly understand how cryptography works.